2D motion of a particle in a central potential. We are starting to look into an important class of problems when particle experiences a force due to a central potential. Since we are talking about 2D motion in a central potential, it's most natural to use polar coordinate system. Potential energy, U, will be just a function of R. Likewise, we know that kinetic energy in terms of polar coordinates will be simply given by mass of the particle over 2 r dot squared plus r times theta dot squared. We can figure out momenta. Since we have 2 coordinates, we expect to have 2 momenta. P sub r, which will be simply partial derivative of kinetic energy with respect to velocity r dot, and that is m r dot, but also theta component of the momentum, which is given by partial derivative of kinetic energy with respect to theta dot, and we find it to be m times r squared theta dot. Thus, we can express the velocity r dot and theta dot in terms of momenta. So let's do it and use Hamiltonian mechanics. In Taylor's textbook, he gives a definition of natural coordinates. Natural coordinates are coordinates that you can write in terms of Cartesian coordinates without involving time. Clearly, cylindrical coordinates are natural coordinates, and for these natural coordinates, we can always write Hamiltonian simply as kinetic energy plus potential energy, but only if natural coordinates. So thus, we write Hamiltonian as mass over 2 radial component of momentum divided by m squared as velocity, then radius squared p theta squared divided by m squared r to the power 4. So both components of the velocity squared and added together, plus u of r. Or after some rearranging, we simplify it to read 1 over 2m pr squared plus p theta squared divided by r squared plus u of r. Now we are ready to generate Hamilton's equations. We expect to have 4 equations, 2 for components of position and 2 for components of momenta. R dot is going to be given by partial derivative of Hamiltonian with respect to p sub r. Theta dot will be given by partial derivative of Hamiltonian with respect to p sub theta. Then radial component of the momentum dot will be given by partial derivative of Hamiltonian with respect to r, and theta component of momentum will be given by partial derivative of Hamiltonian with respect to theta. So we have our Hamilton's equations. What we get from our Hamiltonian is the following. R dot is simply p sub r divided by m. Theta dot is p sub theta divided by m r squared. P sub r dot, here we have 2 terms on the right hand side, p theta squared divided by m r to the 3rd power minus partial derivative of u of r with respect to r. And for p theta dot, we have 0. Since Hamiltonian does not depend on theta, we have a cyclic coordinate, and therefore p theta is constant. P theta is defined as m r squared theta dot, and we will give it a value L. This is, of course, angular momentum conservation. Now we can combine these two equations, and we find that m r double dot is given by minus partial derivative of u with respect to r plus, and here we will use angular momentum value L and rewrite it as L squared divided by m r to the power 3. We recognize the first term here as radial force. The second term we can recognize as centrifugal force. We can use this equation to find r as a function of time. The second equation is theta dot equal constant L divided by mr squared. That equation we can use to find theta of time. A closer look at the radial equation shows us that we now have one-dimensional motion subject to a conservative force. In other words, this equation represents 1D motion in R. The original potential is modified because now we also have the centrifugal force. How do we solve one-dimensional motion when subject to a conservative force? Energy is given as kinetic term plus potential energy, and it's constant. Then we can note that we don't even need to write the equation of motion, because from the conservation of energy we have x dot squared to be 2 over m of energy minus u of x. Therefore, x dot is found to be plus minus square root of 2 over m, and then square root of energy minus u of x, which is itself dx dt. Thus, we have dt, which is given by plus minus m over 2 square root of, then dx, and in the denominator we have energy minus u of x square root of. We can integrate it, and we get that time is given by m over 2 square root of the integral of dx over square root of energy minus u of x, plus, of course, some constant. We see that classically the motion is allowed when full energy is greater than u of x. That gives us restricted domain of motion. For example, if our potential energy u as a function of position x has some dependence on x, and the energy E we see that there are forbidden ranges of motion as well as allowed but restricted domains of motion. The points where full energy is equal to potential energy are known as turning points. When there are two turning points, we have finite range of motion. Here, if the potential energy keeps on decreasing, we only have one turning point. Which means infinite range of motion, or semi-infinite. This motion here, between two turning points, represents oscillatory motion. Period of oscillations for oscillatory motion we have already found. It's going to be given by the integral 2 times m over 2 square root of integrated from point x1, the first turning point, to point x2, the second turning point, of the integral dx over energy minus u of x, which we can further simplify 2 times m square root of. Note that the radial equation of motion that we got had minus du dr for the force plus L squared over mr to the third power. So we can introduce the effective potential that will give us this radial force, the old potential u of r, plus the term responsible for the centrifugal force, L squared, divided by 2 mr squared.